Good morning. It's my great pleasure to welcome you to San Diego State University for the first lecture in the San Diego celebration of the Kyoto Prize. The symposium is made possible by the generosity of the Inamori Foundation. Dr. Inamori, it is an honor to have you here with us today. The Kyoto Prize Symposium is a celebration of the recipients of the Kyoto Prize, Japan's highest private award for lifetime achievement. The prize is presented annually in 3 categories: advanced technology, basic sciences, and arts and philosophy. With our colleagues at Point Loma Nazarene University, the University of San Diego, and UC San Diego, we hope to provide an opportunity for an international audience to learn about the remarkable achievements of our laureates. We are grateful to Dr. Inamori and the Inamori Foundation for providing this occasion to learn about the laureates' extraordinary achievements. And now we'll see a short video describing the nature and the significance of the Kyoto Prize.
The 29th Annual Kyoto Prize ceremonies took place in Kyoto, November 10, 2013. The Kyoto Prize is Japan's highest private award for global achievement. It is given each year by the Inamori Foundation, which was founded in 1984 with the initial private funds of Dr. Kazuo Inamori, founder and chairman emeritus of Kyocera Corporation. Human beings have no higher calling than to strive for the greater good of humanity and society. The Foundation awards 3 prizes annually in the following fields: advanced technology, including electronics, bio and medical technology, material science and engineering, and information science. Basic sciences, including biological, mathematical, earth and planetary sciences, astronomy and astrophysics, and life sciences. And arts and philosophy, music, arts, painting, sculpture, craft, architecture, design, theater, cinema, thought, and ethics. The Kyoto Prize Symposium is held in San Diego, California, to share the ideas of prize laureates across the globe. The philosophy of the Inamori Foundation aims for a future with the proper balance between science, technology, and spiritual maturity, with the goal to contribute to the peace and prosperity of humanity. This is the core mission of the Kyoto Prize.
So before we begin our program, I would like to recognize some of our esteemed guests that we are honored to share this occasion with today. First, we'll start with the 2013 Kyoto Prize laureates, Dr. Robert Heath Dennard, Professor Masatoshi Nei, and Dr. Cecil Taylor, who unfortunately is not able to be with us today. It is also my honor to introduce to you the president of the Inamori Foundation, founder and chairman emeritus of Kyocera Corporation, founder and honorary advisor to KDDI Corporation, and chairman emeritus of Japan Airlines, Dr. Kazuo Inamori. Our next distinguished members of our VIP delegation from Kyoto, Japan include Mr. Toyomi Inamori, Dr. Tisato Kajiyama, Dr. Hiroki Yoshida, Mr. Kaz Emimura, and Dr. Takenori Katsuna. And leading our symposium efforts from our own community, Dr. Rodney Lantham, Director and Treasurer of the Kyoto Symposium Organization. And Mr. Dick Davis, Executive Director of the Kyoto Symposium Organization. And from San Diego State University, I also would like to acknowledge Provost Nancy Marlin. And Mary Ruth Carlton, Vice President for University Relations and Development. And finally, I'd like to recognize the extraordinary SDSU graduate students who have received the Inamori Fellowships this year. If you could rise, please. And now we will show a special video highlighting Dr. Dennard's life's work.
Robert Heath Dennard was born in 1932 in Terrell, Texas, the youngest of 4 children of a dairy farmer and his wife. He enjoyed an active childhood riding horses and climbing trees. Even in his youth, he was always looking for a better way to do things, such as a faster way to chop kindling for the stove. In high school, he played bass horn and excelled in math and science. His guidance counselor suggested he study electrical engineering. In the mid-50s, he attended Southern Methodist University on a band scholarship, where he earned his undergraduate and master's degree in electrical engineering. He earned his PhD from Carnegie Institute of Technology in Pittsburgh in 1958, after which he took a job at IBM. In 1967, still at IBM, Dr. Dennard invented the basic structure of dynamic random access memory, or DRAM. His innovation immensely increased the capacity of digital information storage while drastically reducing its cost. This led to dramatic progress in information and telecommunications technology. Dr. Dennard's invention became the standard of the industry for RAM and enabled the microcomputer revolution. It is now used extensively in all forms of business and personal computers, mobile phones, digital cameras, and many other types of electronic equipment. 7 years later, in 1974, Dr. Dennard and his team proposed design guidelines known as scaling theory, which have become essential to the miniaturization of transistors. They showed that by reducing the dimensions and voltage of a transistor in equal proportions, they could make devices denser, faster, and more power efficient without compromising reliability. Scaling theory started a revolution in digital electronics that continues as a driving force to this day. In 1979, Dr. Dennard was appointed an IBM Fellow. Over the years, he has earned numerous honors for his work. He holds dozens of patents and continues his research work at IBM. He is keenly interested in clean energy and environmental preservation. Dr. Dennard's advice for young people is, education is indispensable in order to be able to make a significant contribution to science and engineering. Realize that what you do can make a difference and take advantage of that.
So it is my very real pleasure today to have the privilege to introduce to you Dr. Heath, who is the laureate winner for the Kyoto Prize for Advanced Technology. So the Kyoto Prize is a very interesting prize in the sense that it's for lifetime achievement. And it also has a very rich philosophy in which it's embedded. You heard some of that philosophy in the video, but I want to read you a couple quotes from Dr. Inamori from the website that describes his philosophy, because in part it sets the context for the award. So Dr. Inamori had 2 reasons for creating the Kyoto Prize. The first was that his belief that we on Earth have no higher calling than to serve the greater good of humanity and society. And he wished to repay the global community that has sustained and nurtured him. The second reason, he said, is he'd like to redress the relative lack of formal recognition for highly dedicated but unsung researchers. So today we're going to sing the praises, and today we're also going to introduce you a little bit more to at least one of our laureates. So with that philosophy in mind, what I'd like to do is turn back to Dr. Dennard and give you a little bit of more specific information than perhaps the video provided. If any of you got up this morning and you answered your email, it turns out Dr. Dennard was helping text with you. As you drove in maybe this morning, maybe perhaps you used your GPS, you had someone helping guide you, and that would be Dr. Dennard. If you played Xbox last night and you won, he shared your victory. If you're in the back of the room doing Facebook on your smartphone, you should probably stop. I think Dr. Dennard would be the first to tell you that he didn't invent the Xbox or GPS or smartphones. But every one of those, when you turn it on, has to go through a process where you load information, you load instructions. Basically, your device is born anew every time you turn it on. It is that connection, it's that memory that allowed those instructions to be learned, which are getting progressively more complicated, progressively bigger. As millions of lines of code are introduced into that device, something had to make that happen, and that's where Dr. Dennard comes into play. So we're going to slide back a little bit in history. In my opinion, not very far back, because it's 1966, and he was a member of the IBM team. At that time, memory was still being done by magnetic tapes, as well as there were some RAM systems. For those who don't know what magnetic tapes look like, I was going to tell you that it's like records, but you don't know that either. So instead, those are the things in science fiction movies that spun around rapidly. At that time, memory cells were created by having 6 transistors and a capacitor. You could have static RAM where memory was fixed in it, but what ultimately happens is with the capacitor, it starts to lose that voltage over time, and you have to constantly be replacing it, which is where they introduced the idea of dynamic RAM, because it's constantly having to be put back in. So Dr. Dennard's idea was to basically find a way to simplify that process. And instead of using 6 transistors, he was able to come up with a configuration that was only 1 transistor. And that simplification was ultimately what created DRAM, which is what we're using currently today in a lot of our systems. Admittedly, there's been a lot of improvement and changes, but it's still that foundational core that he created. With DRAM, what you got was much more capacity, you got a faster set of memory, you got a cheaper form of memory, and also it was energy efficient. So all of those were terrific, and I'm especially fond of the less expensive part. The other thing that he alluded to, which is something that all scientists sort of strive to do, and that's to try to create a general model for things, rather than just a single discovery or a single problem solved. If they can create a pathway, if you will, a set of guidelines, then in fact everyone who follows behind you can follow that pathway and make changes appropriately. So one of the issues as we attempt to shrink the memory chips, if you start to move it down in size, different changes occur that aren't necessarily linear. It's just not the same as shrinking things proportionally. There was rules that needed to be codified. There was changes that needed to be made depending on the size. And all that combination together produces something called scaling theory. So Dr. Dennard contributed really, he could have been into the Inventors Hall of Fame, I think, for just having DRAM, but by the time you combine the two, our debt to him does nothing but increase. How did that translate into practical things for us? Well, we certainly had a changing pricing that's associated with it. In 1980, the approximate cost of a megabyte of DRAM was $6,000. Today, it's about a penny. So that's what I felt. As we continue to push things down, we continue to increase our demand for memory, you can see the two work synergistically to make many of the things that we've become so dependent on successful. In 1976, there was a computer enthusiast who you may have heard of named Steve Wozniak. And he built a user-friendly desktop computer that only had a 4 kilobyte use of the DRAM. It attracted enough interest that someone named Steve Jobs, who you may have also heard of, decided that they would market a computer and develop a company called Apple. And the first machine that actually used the DRAM was the Apple II, which is, again, a little bit in the history. So did Steve Wozniak actually recognize this achievement as significant? Did it mean something, or was it just part of a larger construction that he was doing? So last night, we're at the dinner table, and sharing our table with was Steve Wozniak. He had flown in straight from Norway. His wife flew down from the Bay Area. They stayed through the entire dinner, which not everyone did, and then proceeded to get in their car and then drive through the night to go back to the Bay Area. Did Steve Wozniak recognize the achievement? I think the answer is clearly yes. If you look at his life, what you see is a lifetime of achievements. He has 12 different patents. There's been variations on the DRAM. And having said that, though, the single transistor DRAM is still the current standard after almost 40 years since its original development, which if you think about the rapidly changing semiconductor and computing industry, that's an amazing testament. He's received numerous awards over the years. Not only has he received the Kyoto Laureate Prize, but he also received the U.S. National Medal of Technology and Innovation from President Reagan. He also was inducted into the U.S. National Hall of Fame in 1997, and he received the prestigious IEEE Medal of Honor in 2009. But I think the story is more about achievement. It's about something else. And I'm going to actually steal one of his stories slightly that I heard in Kyoto. And actually, I'm going to actually speak to the students a little bit directly, too. So one of the questions you might have is, why are you here? And what is it you hope to learn? So clearly, one of the things you hope to learn, I hope, is that this is a life of achievement. We're here to celebrate that achievement. But it's also a moment of inspiration. Now, the story I'm going to step on slightly, and he'll expound, I hope, during his regular talk, is that he had gone to a seminar at IBM that was for an unrelated topic. It was a good seminar. I don't think it factually led to any changes in his thinking. But what happened was the speaker ultimately solved a problem in what academics will often call very elegantly, which means very simply. So Dr. Dennard left that meeting, and he asked the question, not so how would he apply to his work, but he thought, why haven't I solved my problem equally elegantly? He was inspired to approach his problem differently by someone else. 2 years later, that idea was patented and ultimately implemented. And so for me, part of what is you're coming here today is not only to learn the factual side of things, but to listen to his life story. What I'm hoping for is that there's someone else in this room who, like he was being inspired, will also be inspired. In essence, what's happening is he's paying forward the inspiration to you that he received from somebody else. In his video, which you ultimately see is Dr. Dennard said, closes with a question and says something like, why does it have to be this way? And his answer, I think, with his life is really, it doesn't have to be this way. And what he does, he found a different way to approach problems than anyone else had approached it. So from a one-room schoolhouse to the Kyoto Prize winner, I think his life provides a very nice narrative of an incredible intellect, a willingness to seek new pathways, and a spirit to try and do more. And now it is my very great honor to introduce our featured speaker, the 2013 Kyoto Prize laureate in Advanced Technology, Dr. Robert Heath Dennard, who will be presenting Reflections on Creativity in My Microelectronics Career.
I want to thank Steve for that wonderful introduction. That was remarkable and really reinforces the message I want to bring to you. I'm very happy to have this opportunity to speak to you. I will talk first about my formative years, my childhood and my education, and then about my most creative years in microelectronics and how microelectronics evolved over the years to have such an astonishing impact on society. I will close with an update of an essay on creativity I was invited to write in the year 2000, looking at opportunities and challenges for the new century and beyond into the new millennium. I was born in a small town in Texas in 1932, in the middle of the Great Depression, to a loving family of very modest means, but great pride. By the time I was growing up, we had moved to a small farm in a rural area in East Texas and lived in a house which did not yet have electricity. My father farmed the fields and raised the livestock, and my mother kept us fed and provided with clean clothes. I started my education in a one-room schoolhouse with 3 grades and different rows of desks. After a couple of years, I moved to a little larger school where my 4th grade class was in the same room with the 5th grade class. Learning came easily to me, so I had a chance to hear what the higher grades were doing and advance at my own pace. My older sisters and brothers had grown up and left home, but they visited frequently and provided great role models. I remember long summers with lots of free time to think and entertain myself. In the early 1940s, when World War II came, my father saw an opportunity to move our family to a small town just outside Dallas. I now attended bigger schools and lived in a community where I could visit and interact with classmates. I also found the library and became an avid reader. When my sister Evangeline went away to become an Army nurse, she left behind her collection of books and phonograph records. I was totally impressed with a large red book which was an anthology of science fiction short stories. I read them all with pleasure, and I particularly enjoyed those by H.G. Wells, which stimulated my young imagination and formed vivid images of strange worlds and people. I was very amused by a book of Ogden Nash poems, which I read and memorized. There was also an album of Sigmund Romberg operettas, which fascinated me. I sang along with them and also memorized the words and tunes. And this was most likely was the starting point for my love of choral singing and all forms of music. While I loved sports and played baseball and touched football with my friends, I was not big enough or fast enough to compete in high school team sports. Luckily, in my sophomore year, a high school band was started, and I became a member. I played French horn at first, and later I switched to a bass horn, which was needed in the marching band. As I was finishing high school, I chose my future career as an electrical engineer with the help of a guidance counselor. She advised me that electrical engineering was a fast-growing field, and she said it would be good for me because of my mathematics aptitude, and attitude also, and my interest in science. I planned to go to a nearby state junior college along with most of my friends. But one day an important thing happened which changed my life. The band director of Southern Methodist University in Dallas came to visit me and offered me a band scholarship to come to this much better school. His advice was, why not take the best opportunity available to you? That was a striking idea to me that helped guide the rest of my life. It helped me go on from SMU to Carnegie Institute of Technology in Pittsburgh, top engineering school, which is now Carnegie Mellon University. And from there, when I got an opportunity to join IBM, at the time its Thomas J. Watson Research Center was just being started, I didn't hesitate. After a long period, after a pretty long learning period in research, I feel very lucky that I got involved in microelectronics in the middle of the 1960s. I would like to tell you something about the invention for which I'm being honored and how it came about and where it fits in the broad context of microelectronics. May we have the slide? This chart by Professor Sa, a pioneer of the field, defines three different phases of microelectronics. Phase one includes the invention of the transistor and its early use as a discrete device replacing a vacuum tube. Phase two began with the concept of the integrated circuit, using microimaging techniques to fabricate many transistors, other components, and the wires connecting them together on a tiny silicon chip. 10 years were taken to develop this technology and actually make it work. The third phase, beginning in 1969, saw the deployment and continuous improvements in microelectronics, which has continued ever since. I first got involved in the second phase of microelectronics in the middle of the 1960s. I was assigned to work in a group at IBM Research which was developing a new kind of transistor called a field effect transistor. These transistors were also called MOS transistors, where MOS stands for metal oxide semiconductor. That name describes their structure, a metal gate over a thin oxide insulator on a semiconductor substrate. My particular small group had the task of learning how to use this newly emerging type of transistor in integrated circuits built on silicon substrates to perform computer functions. The big goal was to replace the magnetic core technology used in those days for random access memory called RAM. In those memories, small loops of magnetic material, very much like beads, were strung together using wires into large two-dimensional arrays. Each of these beads could be magnetized to store 1 bit of data. The largest memory in the largest IBM mainframes at that time was 1 megabyte. The clock rates were hundreds of kilohertz, and the power consumption was about 40 kilowatts. We had a proposed way to build memory with our MOS technology, which used 6 transistors and a flip-flop memory cell to store each bit. We hoped to integrate 128 of these memory cells in a small silicon chip. One day in late 1966, an important event occurred in my life. During the day, I attended a very large IBM research conference where various projects were presented. I was very impressed by the description of a proposed thin film magnetic memory, which was projecting hundreds of thousands of bits in a 25 centimeter wide memory board. What impressed me was, as fundamentally better about their approach, was that they had a very simple memory cell, just a small square of magnetic material at the intersection of 2 etched copper wires. I was inspired to find something that simple for the technology we were developing. I went home that evening pondering analogies between magnetic circuits and electronic circuits. I considered the possibilities for using a simple capacitor as a basic memory element, storing a bit of binary data by charging or discharging the capacitor to 2 different voltage levels. This slide shows the simple circuit I discovered. A capacitor, as suggested by its symbol, is just 2 conducting plates separated by a thin insulator. I found that an MOS transistor in series with each capacitor could be used as a switch to connect the capacitor to a data line briefly to charge or discharge it to write a data bit represented by a positive voltage level plus V or a 0 voltage level on the bit line. The transistor is turned on and off by a control signal on a word line, which allows selecting a given capacitor from many others for receiving the data on that bit line. In my thinking, initially, the capacitor was the gate of another transistor, and the reading was accomplished by monitoring the flow of that second transistor. I was very excited about this idea, but it wasn't as good as I wanted. It required multiple access lines with complicated drive schemes, or an additional transistor to make a memory array function properly. I kept working on various configurations for a few weeks until I finally realized that the stored charge could be read back through the same transistor through which it was written, which would create a small detectable signal on the bit line. The cell had been reduced to a single transistor and a capacitor at the intersection of 2 access lines. I was satisfied this was as close as possible to my goal and offered a great reduction in complexity compared to the 6 transistor memory cell. The drawing on the bottom shows a cross-section of a field effect transistor and a capacitor forming a 1 transistor memory cell. I won't attempt to describe this in detail. A beauty of the integrated circuit is that the conducting layer forming the gate of the transistor is common to all the gates of the other memory cells, so it also serves as the wire selecting a particular row of cells. Also, 1 doping region in the silicon is both the drain electrode of the transistor and one of the capacitor electrodes. A distinctive characteristic of this memory cell is that a small leakage current from the N-doped region you see there to the P-doped region, silicon, discharges the capacitor in a fraction of a second. This gives rise to the name dynamic, since the data is only stored temporarily. To preserve the data, it must be refreshed by reading it out and writing it back into each cell at certain intervals. Fortunately, the speed of this memory scheme allows more than 100 million read or write operations per second. and only a small percentage of these are needed for refreshing the data. Thus, this scheme became known as dynamic RAM and commonly called DRAM. D is for dynamic. I sometimes think it's for Dennard, but, but I'm very modest. This slide shows a drawing from the U.S. patent which I was granted for this work in 1968. It shows a small array of memory cells connected to circuits for supplying the data and for selecting a particular row of cells. My management at IBM understood the potential of this new invention, but it was considered too risky for the technology at that time, which was still leaky and unstable. So I went back to work with a few others to design and prove a prototype of a 512-bit chip using the 6-transistor cell. Later on, this 6-transistor cell came to be called static RAM, after dynamic RAM was named. In time, we completed the research and development work on the NMOS transistor process, wrote up a design manual, and transferred it to manufacturing. Eventually, in the early 1970s, IBM shipped the first computers with semiconductor memories using the more established bipolar transistor process, and the MOS static RAM won out in the next generation because of its greater density. And in the same time period, various versions of dynamic RAM began to appear in the industry, at first with several transistors per cell, like the popular product from Intel. I finally got a chance to work on my one-transistor RAM scheme in 1970 when a new project was started at IBM Research with the ambitious goal of drastically reducing memory costs by combining the simplicity of these one-transistor memory cells with a substantial reduction in all the transistor and wiring dimensions of the integrated circuits. My longtime associate, Dale Critchlow, was the leader of this program. We wanted to take advantage of dramatic advances in lithography techniques which were being developed at our laboratory, such as electron beam pattern writing, which we felt could reduce the dimensions used in integrated circuits by a factor of 5. One of the practical problems we had to face was how to design MOS transistors with such very small dimensions. We knew that just reducing the size caused them to switch on and off poorly. My group responsible for the MOS transistor design considered all the problems, and it soon became clear that there was a general way to design smaller devices which involved scaling down of a few key parameters. This is illustrated in the next slide. We found that reducing the applied voltage, V, and increasing the silicon substrate doping concentration, N, by a certain scaling factor called alpha here in these slides, allows all the dimensions of the MOS devices to be reduced proportionally. The smaller transistor on the right has the same electric field patterns as the transistor on the left, so it behaves in a very similar way and turns on and off properly. Also, we plan to scale down all of the interconnect lines by the same amount to get much denser integrated circuit layouts. It was a remarkably simple and concise concept, yet it was very powerful. It told us our miniaturized circuits would switch faster and also use much less power. Well, we built a lot of very small devices, scaled by a factor of 5, to confirm the theory and to understand its limits. I presented this work at the International Electron Device Conference in Washington in 1972. Just a few months later, at the International Solid State Circuits Conference in 1973, several companies, including IBM, were showing the first early versions of memory chips using my one-transistor dynamic memory cell. The acronym DRAM, well, pronounced DRAM, came to be used for this type of memory. At the same conference, my associate, Dr. H.N. Yu, demonstrated a small array of DRAM memory cells scaled 25 times smaller in area by using electron beam pattern writing. That's 5 times smaller in each dimension, 25 times smaller. Dr. Yu, along with me and other authors, followed up by publishing an experimental 8 kilobit DRAM chip with these deeply scaled dimensions in 1975. This slide shows a greatly magnified photograph of some memory cells in that chip. The light-colored vertical shapes are the aluminum word lines. They're connected to small square features, which are the transistor gates. The horizontal shapes are the bit lines and the top electrode of the capacitors. This next slide shows the cover of an issue of Nikkei Electronics in 1976, which contains a reprint of our 8 kilobit DRAM paper, is described in the upper right corner. Next slide. This slide shows the first page of that reprinted paper about the deeply scaled 8 kilobit DRAM chip. This paper and our related work on scaling have been cited as key factors in the establishment of a large national program in Japan called the VLSI project for very large-scale integration. The impact of that program was huge. I first visited Kyoto to attend a symposium on VLSI technology, an international conference, which is still held in Kyoto or Honolulu on alternating years. Circuit design innovations also played an important role in the development of the dynamic RAM. The main difference between the dynamic RAM and the earlier static RAM was the need to sense very small signals coming from the memory cells onto the bit lines when a given word line was activated, and to write the original voltage levels back into the memory cell after this destructive reading operation. For some time after my invention, I had the notion that I would use off-chip bipolar sense amplifiers like we had used with our previous static RAM chips. Even for the small arrays which were appropriate to the design ground rules of those days, the number of terminals which could be assigned to bit lines represented a big limitation. We knew that on-chip sensing circuits were desirable, but there was very little experience with MOS circuits for sensing small voltages. The variations in the threshold voltage, which is the gate voltage required for turning on the devices, were quite large in those days. One day, Dale Critchlow, my boss, came around to discuss some balanced latch circuits he had heard about, which I believe were being used in touch-actuated keyboards to sense very small changes in capacitance, which would unbalance the latches. Other people were also working on similar latches at this early time. And this slide shows a figure from a paper by Stein and others published in 1972. The sense refresh circuit in the center contains a latch circuit connected to 2 bit lines on opposite sides of the latch. Both bit lines are connected to a large number of DRAM memory cells. Before each memory access, the transistors in the sensing circuit balance the voltage on the 2 latch nodes and the bit lines connected to them to an intermediate voltage level. Then raising the voltage on any word line in this array turns on the transistor and its associated memory cell, causing the capacitor connected to it to charge or discharge a bit line, so the latch is unbalanced in a direction corresponding to the voltage stored in the memory cell. The beautiful thing about a latch, this latch, when it's activated, is that the small signal unbalance is amplified up to the full digital levels. Those levels are fed right back onto the bit lines where they're written back into the memory cells to restore the original levels. This seems to me to be one of the most fortuitously efficient circuits ever devised. As far as I know, the balanced latch has been used in one form or another in all 1 transistor DRAM cells after the first 4 kilobit chips. There have been many improvements and variations. The next slide shows the de facto standard for many generations of DRAMs. It's called a folding bitline arrangement, invented by my esteemed colleague, Dr. Kiyu Ito at Hitachi in 1974. He took the 2 bit lines shown on opposite sides of the latch in the previous drawing and folded one over to to the opposite side along with its word lines and DRAM cells to form pairs of bit lines being crossed by pairs of word lines as seen in this slide. The advantage he discovered is that noise is introduced on the pair of bit lines are effectively canceled out in this arrangement. Starting in the new topic. Starting in the middle 1970s, our group in IBM Research, led by Dr. Critchlow, worked closely with a manufacturing team in Burlington, Vermont, to develop IBM's first one-transistor DRAM product, shown in this next slide. The technology developed for this chip was scaled sufficiently to be able to produce a 64 kilobit chip. The sense amplifiers shown on this slide were based on a new self-compensating design technique invented by my associate Dominic Spampanato and myself. I also contributed to a new technique for adding redundant bit lines and word lines, which can be used to replace defective lines to greatly improve manufacturing yield. This technique has been widely used for both DRAM and static RAM for many generations since then. I'd like to talk next about what I call a midlife crisis. I was asked to identify difficult challenges in the progression of my work. Just at the time the production of these 64 kilobit chips were being announced and the dynamic RAM seemed to be getting very mature, the world was becoming aware of two very significant papers. May and Woods of Intel and Yaney, Nelson, and Van Skyke of Bell Laboratories revealed that some 16 kilobit dynamic RAMs were suffering transient errors due to bombardment by alpha particles. The alpha particles were identified as coming from radioactive impurities in the materials of the hermetically sealed packages. At first, it seemed like a simple solution. Why not modify the package or introduce a barrier layer, such as a plastic film between the chip and the package? When experiments like these were done in various labs, the error rates dropped substantially, but did not go away totally, presumably due to radioactive impurities in the on-chip materials. Also, an analysis of the possible soft error rates due to cosmic rays showed that this source could be significant. Here was a real crisis. Not only were hordes of people scurrying around to fix up designs then in manufacturing or development, but the whole future of miniaturized MOS transistor circuits seemed to be in jeopardy. Personally, I felt very responsible because of my early role with dynamic RAM and because I failed to anticipate the problem. Several years earlier, I had discussed the possible effects of cosmic rays on dynamic RAMs with an old friend who was knowledgeable about space electronics, but we had concluded that most of the radiation types would pass through the silicon with little effect. After a long period of doing measurements, developing models, and inventing possible cures, a less threatening view of alpha particles and cosmic rays emerged. A good quantitative understanding was provided by various modeling techniques which were developed, including a very powerful Monte Carlo approach developed in my team by George Sai-Halas. It was shown that error rates would rise in response to scaling to smaller dimensions, but that design changes, including error correction techniques, would contain the problem. So the midlife crisis was over. As the idea of scaling MOS transistors with all the layout dimensions, interconnect lines, etc., caught on quickly, the microelectronics industry developed a pace for doing this, which has given rise to the geometric growth in computer capability since then. Moreover, DRAM became the large volume, predictable product which drove scaling in silicon chip manufacturing for many years. By now, I'm sure you understand that DRAM has experienced tremendous productivity increases, which has allowed quadrupling the number of bits per chip every 3 years for many generations. This figure shows pictures of 6 generations of IBM chips and shows the reduction in cell size on that red arrow going through there, which allowed the increased number of bits. Much of this reduction is due to decreasing all the dimensions of the transistors and wires using the scaling principles. The DRAM cell has been compacted further by making technology improvements which reduce the memory cell area. This next slide shows a big breakthrough started by Dr. Hideo Tsunami when he published a paper showing DRAM with a three-dimensional capacitor formed in a trench etched in the silicon substrate. Starting with a 4 megabit chip, all the DRAM produced by IBM has used a trench capacitor technology. Another three-dimensional capacitor structure called the stacked capacitor is fabricated above the silicon surface rather than below. This technique was pioneered by Dr. Mitsumasa Koyanagi and has been used widely in the DRAM industry. This is a good place to introduce a special picture made at the 2006 annual awards ceremony of IEEE, the Worldwide Professional Society for Electronics Engineers. This picture shows from the left to the right Dr. Ito, Dr. Tsunami, me, and Dr. Koyanagi. They were being honored with the Junichi Nishizawa Medal, and I came to celebrate along with them. Notice the fanciful caption. Is it projecting here? Yes. The DRAM father and his 3 sons in scaling law. I believe it was supplied by Dr. Tsunami. That was a wonderful night. And not long after that, we all wrote articles for a very special issue of the IEEE Solid State Society News, which was totally dedicated to DRAM. You may have noticed that part of the DRAM productivity increase has been due to using larger silicon chips. This has required larger silicon substrates called wafers. They were called wafers. When they were small, that was very appropriate. For best manufacturing efficiency, they were made larger as illustrated in the next slide. Over the first 30-year period, the silicon wafer diameter increased from 25 millimeters to 200 millimeters, as shown here. Since then, most of the new factories have used 300 millimeter wafers, as shown in this photograph. I hope you realize how it feels for me to hold one of these wafers. It's actually very light, about the same weight as a quarter pounder. Today's 300 millimeter wafers contain hundreds of 4 gigabit DRAM chips. As you can see in this picture, I'm very proud of what I helped get started. The growth in size of the chips and the increasing number of transistors and circuit elements on a chip followed the path known as Moore's Law, which is named after Gordon Moore, one of the Intel founders who predicted it in the early days. As the complexity of these chips increased, it became very difficult to implement all the numerous wiring interconnections among the transistors, the logic circuit inputs and the logic circuit outputs. It became necessary to provide multiple layers of wires. These were organized with all the wires on one layer running perpendicular to the wires on the next level, just like streets or avenues in Manhattan in New York City. As scaling progressed from one generation of chips to the next, the widths of all the wires were scaled down, along with the transistor dimensions, as the scaling principles we discussed earlier suggested. This made the wires much more resistive for a given length of wire. Some of the wires which had to connect longer distances across the bigger chips got very resistive, and the signals propagated very slowly on those wires. Many people thought scaling was nearing an end because of this problem. To me, it was another crisis that needed attention. I remember giving some lectures at Stanford University in the late 1970s where I proposed the hierarchical wiring system illustrated here. The highly scaled small wiring layers next to the transistors and the silicon substrate can be used for they're only used for very local connections of elementary logic circuits. Wiring layers in the middle with thicker and wider metal lines have much lower resistance, so they can be used for long connections between different blocks of circuits. Very large and thick wires in the top layer can carry high-speed signals all the way across the big chips to connect various processor functions and memory subsystems together. Other thicker wire layers at the top can be used to bring in power for the chip and to distribute clock signals across the whole chip to synchronize the processor functions. A lot of analysis and modeling was done at Stanford and elsewhere to show that such a system can work. It's been in use for many generations of MOS technology, gradually adding more layers with even smaller wires at the bottom and even larger and thicker wires at the top. Also, a new set of materials were introduced with copper wires for lower resistance and better insulator materials for lower capacitance. This picture shows a highly magnified cross-section across the wiring layers in a chip with the new copper wires first introduced by IBM. You can clearly see the smaller wires in the lower wiring planes and the larger wires in the top planes. And here is a scanning tunneling microscope picture with all the insulators stripped away to show some of the lower level wires with the where in one direction they're connected to wires in the perpendicular direction. And today's largest processor chips have as many as 14 wiring layers. And the billions of interconnections use a total of about 40 kilometers of copper wire. The wires are truly as important as the transistors in making integrated circuits work. Since I became an IBM Fellow in 1979, my career after that has been spent on helping DRAM and scaling continue to advance and generalizing the scaling rules in certain respects and finding ways to live with the scaling limitations we were already able to predict in 1972. These limitations include the increased need for material with better conductivity and the inability to scale voltage much below 1 volt and still have the transistors switch on and off cleanly. These problems have caused a leveling off in processor speed over the last 10 years. Work has continued to bring in improved structures to allow further scaling down of transistor and wire dimensions. The main goal now is to improve energy efficiency, to allow large data centers with thousands to millions of processors to provide more computing for a given amount of energy. I plan to discuss this issue and what I see as the best technical path towards solving it in a technical talk here on Thursday. Summing up this part of my talk, I'm very proud to say that with many process improvements, structural innovations, and plain hard work, the thousands of people who make up this industry have been able to achieve in 40 years a reduction in all dimensions of integrated circuits by a factor of about 150, and more is still expected. The result of that, the way the computers have advanced and changed our lives, has been truly amazing. Can you imagine? I used a slide rule to design my first memory chip. The point of bringing that up is to ask a question. What will the world be like in another 40 years? That's the challenge and opportunity for the young people in the audience here today and just starting their careers. You also have a chance to create a greatly different world in your time. Now I'm going to close with some general thoughts about creativity and challenges for the future. The tremendous progress in science and technology in the last millennium and its rapid acceleration in the last century is due to the remarkable creativity of mankind. Yet so little is known about creativity. What is it? Who has it? How can it be stimulated? Apparently so little is known and understood about this subject that it's assumed a person like me with some demonstrated record of accomplishment and creativity can say something interesting and useful about it. So I've decided to suspend my normal humility and accept the challenge to talk about my own personal thoughts and experiences in this area. Above all, creative people cannot resist a challenge. So what is creativity? It's an intellectual capability of some human beings, something goes on in the brain, something not yet matched by computers. And according to my understanding, it's the ability to produce or bring it into existence something that was not there before, something new, an extension of our base of knowledge. In other words, for those of us who have undertaken research as a career, it's a necessary trait to excel in our jobs. Most of my experience has been with the extension of scientific or engineering knowledge and capability, but I suppose some of my observations may apply to artistic fields as well. My experience with creativity is that it can produce a sudden leap into the new and previously unknown. I often wake up in the middle of the night with a solution to a problem which I have been working on previously. Many inventors have described similar experiences to me, including getting out of bed to make notes or drawings before going back to sleep. Others have described significant inventions made while driving, which apparently leaves a lot of the mind free, at least before cell phones. As I previously described, my invention of the DRAM memory cell came early one evening after I came home stimulated and challenged from listening to a talk about a competing research project. The basic idea came in a moment, but there were a couple of months of perfecting it before the final simplification to a single transistor came in another flash of inspiration. Who has creativity? I know from experience in following careers of associates in similar environments over long periods of time that some are creative and others are not. The ones who are not creative can be equal or superior in analytical capability, well organized, good communicators, and overall very useful and solid individuals. But research institutions are measured on their creative output. So it would be good to be able to identify creativity in employment candidates. I believe that creative thinking is basically a process of posing significant questions and finding good answers. So I give a lot of credit in interviews to those who ask relevant, penetrating questions. And I also try to examine their ability to apply fundamentals to answer those questions. I know there have been attempts to develop profiles of creative people using questionnaires, but I don't know how successful those have been. I've been fortunate in recent years to be included in groups of people who have received major honors for significant creative achievements, and I find them very interesting, but apparently ordinary people. At a National Inventors Hall of Fame event, while I was talking with 4 other inductees, I discovered that all 5 of us were raised in rural areas or small towns, and most started their education in one-room schoolhouses. We all were left on our own with a lot of free time to develop our ideas about life. And now that may not be the key to our subsequent successes, but it surely is a counter-argument to many of the things which are considered necessary for the younger generation today. I developed a very slow thinking process in my early days, and I believe that that is why I am able to bring great concentration to a problem and engage my whole brain in finding a creative solution. So how can creativity be nurtured and stimulated? I have a motto posted in my bedroom where I see it every morning, which reads, "Attitude is everything." It was given to me by my ballroom dance teacher, but it applies to many other pursuits. I believe it is the key to unleashing creativity. A great many have the intelligence, many have the preparation, some are at the right place at the right time, and only a few realize that they have the mission and ability to make a major difference in our world. I believe my attitude was developed with the aid of some influential people at each step who urged me to pursue the best opportunity which was available. At the PhD level, my thesis advisor made me aware that I was expected to become the world's expert in the subject of my research. When I joined IBM in the late 1950s, there was a clear mission to advance the computer art. We were issued engineering notebooks to record our patentable ideas and told to invent. Our early projects, in hindsight, were a little far-fetched, but we pursued them with great enthusiasm. And in the middle 1960s, as I told you before, some of us were assigned to do the engineering for a modest-sized program trying to exploit the very new MOS technology. It was a tough technology, but it had great potential if we could solve the problems. My manager told me to find the best way to do memory with this technology. I was ready. I had a very good attitude. I had been groomed and motivated at every step. I was working on the right project at the right time, and I knew my mission. Today, of course, times have changed, and the technical opportunities are in different areas. Is there still a need for creativity? Yes, of course. In a general sense, the need for creativity in the future is obvious. On the other hand, if we look in some detail at where the world appears to be headed, we can readily see that the need is indeed critical. The rapid pace of industrialization of the previously undeveloped nations, and underdeveloped nations, I should say, and the projected growth of populations is leading us to a time where there will be severe impact on the resources and environment of our finite globe. Surely future generations must be preoccupied with understanding and mitigating those effects. Major advances are clearly needed in energy supply and distribution. We must face a crisis of both limited supply of energy resources and major environmental deterioration due to using it. The field of transportation, which has seen such major growth in the recent past, is clearly not on a course which is scalable to the future needs of society due to its very high energy demands. Also, the really big problems of the past remain. Future generations must still face disease, hostile fellow humans, and natural disasters of this tumultuous earth and our chaotic universe. These challenges present a broad range of opportunity for creative solutions, where meaningful goals can range from complete cures to merely improving chances of survival. Are there needs for further creativity in information technology, the means for generating, distributing, and presenting information after the major advances in the last half century? Yes, because these tools have become indispensable to economic productivity and can play a major role in the solutions to the important problems which I described. Where will creativity lead in the future? Every trend curve says that the pace in science and technology, like the stock market, will move ever upward and forward, onward. But we, like every preceding generation, have done everything we know how to do and are unable to see much beyond the next steps, which are already in place. We must also consider the possibility that our last century's prodigious progress has seriously depleted the pool of unknown knowledge left for future scientists to bring forth. Clearly, it appears there are a limited number of laws of physics and chemistry governing our universe and a limited number of basic elements. We may be close to completing our understanding of the essential implications and properties of all of these. Therefore, the future may not hold surprises so fundamental as the radio and the transistor. However, the advances of the future in the physical sciences will likely still be astonishing in their impact on society. Hopefully, this will include some breakthroughs that allow nuclear energy to be fully harnessed. Also, computers will likely be devised with so much creative capability that the question of whether they think will become irrelevant. The biological sciences appear to be breaking forth into their golden age, and the questions there are not how far they can go, but how far should they go. In summary, whether or not we understand exactly how creativity in humans comes about, its impact on the world we live in is profound. I'm optimistic that our creativity will give us the knowledge and tools to clean up the major messes and avoid the potential disasters that our technology advances have spawned. Clearly, more than science and technology will be needed in this respect. Hopefully, the global infrastructure, which my generation of science and technology has provided, will help solve the critical global problems facing future generations. In closing, I want to thank the Inamori Foundation once again for this great honor. And thank you.